Welcome to Chapter 9.1. We're going to cover nuclear magnetic resonance, or NMR for short. Now, Chapter 9 follows Chapter 2, and this is because we want to try and match the new knowledge that you have of functional groups and IR with this new spectroscopic technique. This is how biologists and chemists make use of a range of spectroscopic techniques when either characterizing, monitoring reactions, or determining the structure of an unknown compound. Remember, spectroscopy itself is the study of the interaction of energy with matter. Last time we looked at infrared radiation, and this time we'll be looking at radio frequency radiation, or commonly known as radio waves. These have a lower energy than the corresponding infrared radiation. Let's get started. There will be two videos in this lecture sequence. The first goes through the physical basis of NMR. The second video is a short overview of the features of an NMR spectrum. The learning outcomes, as per usual, are in your handout and are displayed on this slide for 5 seconds before the video moves on. As a brief overview of this spectroscopic technique, a sample tube containing an organic molecule is placed into an NMR machine, which is essentially a radio in a magnet. One of the coils generates electromagnetic radiation, i.e. radio waves, which sweeps a range of frequencies, and at a certain point, we'll discuss this at greater length, a signal is emitted by the sample and is picked up by the receiver. These signals become small electrical currents which are processed by a computer and produce an NMR spectrum. Let's take a look at what is happening to a molecule of the sample as it becomes excited. We've seen this diagram before when we looked at the process of absorption when IR was absorbed and caused molecules to vibrate, or rather bonds in a molecule to vibrate. The idea here is similar for NMR spectroscopy, but this time, rather than there being a focus on the electrons in a bond or their movement, the focus shifts to a particular nucleus in our molecule, which continually absorbs radio waves and only becomes excited when a specific frequency is absorbed. Now, because energy is quantized, when the nuclei in the molecule relaxes, there will be an emission of energy, which corresponds to the same frequency that the nuclei of our molecule absorbed in the first place. On this course, we'll be focusing on the hydrogen atoms, or protons, in these molecules. This is because the nuclei of these atoms possess a property called spin. Let's take a look at the hydrogen atom and explain how NMR machines exploit this property. Hydrogen atoms are an integral part of an organic molecule and can feature in the simplest amino acid monomer right through to really complicated protein structures, such as that of an enzyme. Being able to tell the environment of the hydrogen atom and what it is connected to is part of a biologist or chemist toolkit in structural elucidation. However, in order for NMR to work, it relies on atoms being comprised of an odd number of protons and neutrons, otherwise their spin cancels. A hydrogen atom is comprised of one proton and one electron. The electron is not really orbiting the nucleus like this, it is in an electron cloud surrounding the nucleus as represented here. We're really only interested in the single proton of the nucleus, however. So what is this property called spin anyway? Well, a hydrogen's proton is a charged particle, and this generates its own magnetic field. Protons, neutrons and electrons can spin on their axis in either an upward or downward configuration. Think of the north-south poles of a magnet. This creates a magnetic dipole or magnetic moment. As shown on the right, the proton in a hydrogen atom spins on its axis. Where the nucleus contains more than one nucleon, that's neutron and proton, their spins are paired so that they can cancel out. However, in a nucleus with odd numbers of nucleons, like our hydrogen atom, that's 0 neutrons and 1 proton, the nucleus always has a permanent overall spin. So, the protons of a sample organic molecule, that's the hydrogen atoms, remember, Each behaves like its own tiny magnet and will have a random orientation when not exposed to a magnetic field. However, once we put an organic sample into an NMR machine, you're placing each of these tiny magnets into an external field that is generated by the NMR machine. What do you think will happen to each of these protons with respect to that external magnetic field? Pause the video and resume when you have an answer. Think of what happens when you place a compass needle near a magnet. The arrows represent the magnetic moments. There are two possible alignments of each of our tiny magnets, or protons. Either they can be aligned with the external magnetic field, which we call B0, and this is a lower energy state, called the alpha spin state. Most of our protons will now be in this spin state. However, very few of the protons might be aligned against the external magnetic field, and these are in the excited beta spin state. At a magnetic field strength of B0, the sample is pulsed with radio waves with a different range of frequencies, and when that frequency matches the energy required to flip the spin from an alpha spin state to a beta spin state, this gives rise to the phenomena known as resonance, where the spin changes from being aligned with the magnetic field to being aligned now against the magnetic field. And of course, this is not permanent, and once the pulse stops, the hydrogen nuclei relax. When they relax, then the NMR machine is used to record the energy emitted. That's radio frequency radiation in the form of a tiny current, which is processed by a computer after the NMR experiment. Since protons all have the same magnetic moment, we might expect reasonably that all hydrogen atoms give resonance signals at the same field or frequency values. Unfortunately, for chemistry applications, that's not true. Why should the protons in a molecule behave differently in the NMR experiment? Pause the video and resume when you have an answer. The answer to this question lies with the electron density surrounding those protons in the molecule. They're not the same. Since electrons are charged particles, they move in a response to the external magnetic field, B0, that was applied by the NMR machine. And this generates a secondary field that opposes the applied field, B0. This secondary magnetic field generated by the electrons shield the protons from the applied field, and so the electron density around the protons is what dictates whether or not they're in a electron-rich or electron-poor environment. So protons in an electron-rich environment require radio frequency with a lower energy to achieve the beta spin state, and hence energy to resonate. This is E2 on our diagram. Remember, the dipole has to be in the opposite direction to the applied field, B0, seen in blue. However, protons that are deshielded or have very little electron density require either two things to get them to resonate. That's flip the spin from the alpha state to the beta state. Either B0, which is the magnetic field strength of the NMR machine, is increased in order to achieve resonance, or the radio frequency used to pulse the sample is increased as it will have a higher energy. Signals A and B are processed by the NMR machine and produce two different signals at different energies. Now, on our diagram we can see that signal A corresponds to energy 1, where the proton environment was deshielded, whereas signal B corresponds to energy state 2, where the proton environment was shielded by those electrons. Now, E1 is greater than E2 because we need to see where 0 is on the spectrum. Now, there are two ways of running the NMR experiment, and they include varying or sweeping the magnetic field over a small range while observing the radio frequency signal from the sample, or equally, there's an effective technique whereby the frequency of the radio wave radiation is increased while holding the external magnetic field constant. Regardless of the choice of NMR experiment, we're usually interested in the outcome, which is the NMR spectrum itself, and it looks a bit different to the mock-up we have on this diagram.
This concludes part A.
Now that we've explored the physical basis of producing a proton NMR, let's see what one looks like and briefly examine some of its features. Firstly, the scale is given in parts per million. Instead of designating a range of NMR signals in terms of magnetic field differences, it's more common to use a frequency scale, even though the NMR spectrometer may operate by sweeping the magnetic field. Most organic compounds exhibit proton resonances or chemical shifts that fall within a 0 to 12 part per million range. Also, like IR, the scale has the higher numbers on the left and the lower numbers on the right. NMR requires the use of an internal reference compound that always sets this scale to 0. This is called tetramethylsilane and has the abbreviation TMS. What other information can we glean from this NMR spectrum? Note, except the internal reference, there are two NMR signals. Now this gives us our first piece of information, the number of chemical environments, and matches the number of chemical environments in bromoethane. That is 2, one blue and one pink. Each of these signals occur at a different chemical shift, and we'll be discussing why this is in the next chapter. The good news for us is that these chemical shifts provide clues about the environment of those protons with respect to their neighbour or neighbours. The next piece of information is the integral. The area beneath each signal correlates with the number of protons in that particular chemical environment. For the pink signal, the area under the signal is free and matches the number of protons highlighted in pink. Finally, note how each signal is split into individual peaks. This signal splitting is another incredibly useful piece of information called the multiplicity of the signal. The splitting of the signal reveals the number of neighbouring protons. All three are key pieces of information that you can use to solve the structure of a molecule. Each of these pieces of information will be considered in videos of the next lecture, Chapter 9.2. Join me there.